If you're driving a speeding car and slam on the brakes, the vehicle stops, but your body wants to keep moving forward. That exact same physics applies to the rock we live on. At the equator, the Earth is rotating at over 1,000 miles per hour. If that rotation were to instantly drop to zero, absolutely everything on the surface would maintain that immense forward momentum. You wouldn't fly off into space. The escape velocity is far too high for that, but you would be violently hurled eastward. In a crowded market, every single cart, piece of inventory, and person suddenly becomes a lethal projectile moving at supersonic speeds. And it doesn't matter if you're standing out in the open country. A multi-ton mechanical thresher sitting in a field would be launched through the air as effortlessly as a handful of wheat. This animated 3D globe illustrates the anomaly perfectly. The solid crust of the planet has halted, but the atmosphere, the oceans, and absolutely anything not bolted deep into bedrock continue to sweep horizontally across the surface at their original speed. The initial halt is merely the trigger. The true catastrophe lies in the atmosphere and everything on the surface becoming a supersonic debris field, shredded by their own momentum. While the ground underneath you is suddenly stationary, the air above it isn't. The atmosphere retains its massive rotational energy, generating continuous surface winds of 1,670 kilometers per hour, right at the equator. The fastest wind speed ever recorded on Earth was around 400 kilometers per hour. These equatorial winds are over 4 times as strong. They would instantly shear the facade off any skyscraper and grind steel-reinforced concrete down to dust, effectively scouring the crust clean. If you live further north or south in the mid-latitudes, the Earth's rotation is slightly slower, which means the resulting winds are too. But an 1,180 km/h gust ripping through Chicago's Marina City towers would still snap them like twigs. Escaping to the countryside offers zero geographic protection. A serene valley might not have buildings to collapse, but these winds are strong enough to rip mature trees out by the roots and strip the topsoil straight off the hills. Surviving the physical shock of the planet halting is ultimately irrelevant. Within seconds, the atmosphere itself operates like a supersonic sandblaster, leaving no safe haven anywhere on land. To understand what happens to the oceans, take a look at this cross-section of the Earth. The centrifugal force generated by the planet's spin naturally pulls massive amounts of ocean water toward the equator, creating a continuous global bulge. The millisecond the spin stops, that outward force vanishes. Gravity takes over, and all that equatorial water immediately seeks the center of the Earth, which is geometrically closer at the North and South poles. The oceans rapidly drain away from the middle of the globe. Coastal cities like Boston sit in the direct path of the surge, destined to be consumed by a wall of polar-bound water moving 17 miles inland. The mass exodus of the oceans would displace so much water that a continuous ring of dry land would emerge around the equator. The planet would effectively be split by a single massive supercontinent dividing 2 mega-oceans. Our hypothetical experiment only lasts for 5 seconds. When those 5 seconds are up and the planet abruptly snaps back to its full rotational speed, the sudden torque applies massive force to the crust. Tectonic plates shatter and grind against each other, triggering global earthquakes and instantaneous volcanic eruptions. The oceans, which just arrived at the poles, are immediately yanked back toward the equator by the returning centrifugal force. Whatever fragments of land survived the winds and the first tsunami are completely obliterated by a second reverse wave, effectively resetting the planet's surface. But let's assume the Earth never restarts. What if that 5-second halt stretched into an eternity? The surface destruction would be absolute, but the deep planetary mechanics would trigger a much slower extinction. This dual hemisphere model shows what happens when we lose the day and night cycle. A single day would now last an entire year. One half of the globe would bake under 6 months of continuous, scorching sunlight, while the other half freezes in absolute darkness. Beneath the crust, the Earth's spinning liquid iron core acts as a massive dynamo. Without rotation, that dynamo stops, and as you can see here, the magnetic lines shielding our planet dissolve, leaving us entirely exposed. Free from magnetic deflection, brutal solar winds would slam directly into the atmosphere, rapidly tearing away the ozone layer. Deadly cosmic rays would blanket the surface, breaking down the DNA of whatever organisms managed to survive the initial floods. Without the dynamic forces of a continuous spin, our vibrant biosphere collapses. The Earth would slowly bleed off its atmosphere and water, eventually becoming a sterilized, irradiated rock, entirely indistinguishable from Mars. You can take a breath. The planet isn't going to slam on the brakes today, or tomorrow. However, looking at this magnified data chart, the Earth is technically slowing down. Thanks to tidal friction, our days have gotten longer over the last century, but we're only losing about 1.7 milliseconds every 100 years. At that rate, it would take roughly 18.5 billion years for the planet to naturally grind to a complete halt. Long before that happens, the sun will run out of fuel, expand into a red giant, and swallow the Earth whole. Every ocean current, every weather pattern, and every breath we take relies entirely on this silent, billion-year-old spin. It's a cosmic balancing act that we take completely for granted, at least until we stop and imagine the alternative.